we have these two molecules and we're measuring the distance between them as they interact with each other, we're typically going to be measuring from center to center. So this distance from center to center is called R, R for radius. And we call this a radial distance because it's measured from the center. In general, any distance measured outwards from some central point is referred to as a radial distance. So R is the radial distance from center to center. And we're going to be measuring this in units of sigma. Sigma is the diameter of one molecule. The Greek letter sigma. And so we'll be describing, for instance, this distance here, 1, 2, 3, this is about 3 sigma. So because the distance from center to center is about 3 times as large as the diameter of the molecule, we'd say R is about 3 sigma. And so this is just a convenient unit of measurement. Typically, sigma will be some specific tiny number of meters, like maybe sigma equals 2 times 10 to the negative 21st meters or something like that. And that'll typically either be given or maybe we don't even care about it. But the thing is, since sigma is just some specific value for that type of molecule, we can measure all the distances in units of sigma and just do all the calculations as if sigma was the unit of measurement we're using. And then at the very end, if we need to, we can replace sigma with whatever value is for that molecule. Of course, it's going to be different for different types of molecules. Any questions on the terminology used for distance so far? And if the molecules are really close, like let's say the molecules are so close that they're essentially touching, they're basically overlapping each other almost. In that case, what would be the distance from center to center? If they're actually just barely touching at their outer edges, what would we call that distance? If sigma is the diameter, how far is it from center out to the edge? How far would one radius be? Yeah, that would be half of sigma. So this distance is half of sigma. And this distance, center to edge, is also half of sigma. So what would the actual distance from center to center be? Yeah, 1 sigma. So if the radial distance, the distance from center to center, is exactly 1 sigma, then the molecules are so close that they're essentially touching. They're almost overlapping. And in that case, what would you expect to happen? If you push molecules that close to each other, what would you expect those molecules to do to each other? What do you usually find in the outer edges, the outer regions of a molecule or an atom? What kind of particles do you find in the outer edges? Yeah, electrons. If you take a look at where the charges are, we've got negatively charged electrons in the outer shells and the positively charged protons and neutral neutrons concentrated in the nucleus in the center. So that means if these molecules are getting really close to each other, if they're far apart, then the electric forces don't really matter because they're neutrally charged overall, same number of positive and negatives. But if they're really close, the negatives in the electron shell are getting really close to each other. What happens if you got negative charges really close to negative charges? Yeah, they're going to repulse. They're going to repel each other. So that means if you get the molecules too close to each other, they're going to repel. The electric forces of the electron shells almost overlapping repel each other. I think if they get really close, the Pauli exclusion principle might kick in also, that you've got electrons trying to overlap the same space and they can't do that. So if they're too close, the molecules are going to repel. They get a force pushing outwards. So let's write this down. Let's write down some facts about force. Force facts. We know that if the molecules are too close, they're going to repel each other. If they're too close, we get a repulsive force. And if the force is trying to repel them, trying to push them away from each other, would you treat that as the positive direction or the negative direction for a force? What's that force trying to do to the value of R? If you get a repulsive force, if the molecules are repelling each other, is that trying to make R increase or decrease? Yeah, the repulsive force is trying to increase R, so we call that a positive change. So a repulsive force we treat as a positive value for force. Force is greater than 0. So positive force means a force that's trying to increase some value, specifically trying to increase R. So that means a positive force is a repulsive force. On the other hand, if they're further apart from each other, let's say we have these molecules far apart. Not really far apart, but just kind of far apart. Like, let's say they're just some distance, maybe 3 sigma apart from each other. In your experience, not in physics, not in a lab, not in chemistry, just in everyday life, in your everyday experience, does matter tend to clump together or does matter tend to fall apart? Like this marker board here. Is this marker board falling apart into individual molecules, or are the molecules tending to stay together? Yeah, they're sticking together. Molecules don't repel each other forever. If they're too close, they do repel each other. But as long as they're not too close, they should be attracting each other. They should be clumping together. This is why we have matter and things in the universe instead of just a diffuse cloud of hot hydrogen gas really far apart. So the reason why we have things in the universe is because matter tends to clump together. Molecules attract each other as long as they're not too close. So if these molecules are not too close together, they're a little bit far apart, they get an attractive force. Molecule A pulls molecule B to the left, and molecule B pulls molecule A to the right. These are the equal and opposite forces, equal strength but opposite direction, that we're going to be looking at in more detail in 7b. But for now, if we just got a force that's pulling them together, what's that force trying to do to the value of R? Yeah, that force is trying to decrease the value of R, so we would call that force what sort of value? Yeah, it's trying to make a negative change. It's trying to decrease the value of R, so we're going to call that attractive force a negative value. So if the molecules are kind of far apart, not too far apart, but kind of far apart, we get an attractive force. And we call that force negative. Force is less than 0. Because it's trying to decrease the distance. It's trying to make a negative change in the distance between them. So if they're too close, they repel. If they're kind of far, they attract. And this is really because this is a blend of several different forces. You've got the electric force of the electrons trying to repel each other. You've got, I think it's called the van der Waals force from chemistry, trying to make them clump together. And maybe some other forces as well. But we don't really care about the individual forces. We just care about the total force and whether that's attracting or repelling. If we've got repulsive forces if they're too close, which switches over to attractive forces if they're further away, what has to be happening somewhere between too close and kind of far? If they're too close together, they repel. If they're too far apart, they attract. Yeah, somewhere in between, there's got to be equilibrium. There's got to be some sweet spot distance where the attractive forces and repulsive forces cancel each other out. And at that distance, there's no force at all in total. Of course, there are forces, but the total force would be 0. So there's going to be some sort of equilibrium distance between too close and kind of far, where the force is 0. All the forces cancel out. Also, what would you expect to happen to this attractive force if the particles get really far apart? As the particles get further and further apart, what would you expect to happen to that attractive force? It's eventually going to be gone. Technically, it'll never be truly gone entirely. No matter how far these particles are from each other, there's always going to be some attractive force between them, but it's going to get weaker and weaker the further they get. As these particles get further apart from each other, the attractive force gets weaker and weaker and weaker. When they're really far apart, the force is still there, but it's so small that it may as well be 0. Especially since these are probably interacting with other things in the universe as well. And those other forces are probably going to be stronger than this extremely weak attractive force. So when they're really far apart, the attractive force gets very close to 0. So when they're very far, the force is approximately 0. Any questions on that so far? All this stuff about the forces. And thanks to a certain equation we were looking at earlier, every one of these facts about force can also be translated into a fact about a potential energy graph. Yes, if we're exactly at equilibrium, if we're exactly the right distance apart from each other, then the force is going to be 0. Or rather, the total force is going to be 0. The forces that are happening cancel each other out at that distance. And that distance, we already said that if they're exactly 1 sigma apart from each other, the force is going to be repulsive. But if they're a little bit further out, equilibrium is that distance plus a little bit extra. So if they're a little bit further out, if they're not quite touching, the distance there, once again, we have half sigma for the radius. We've got another half sigma for this radius, plus a little bit extra. So the actual distance for equilibrium, which we're going to call r sub 0, so that's a little bit further out than too close, but not so far out that it's attractive. So we've got sigma over 2 plus sigma over 2. That gives us 1 sigma plus a little bit extra. So R naught is going to be 1 sigma plus a little bit extra. And it turns out that that little bit extra is about an extra 0.12 sigma. So R naught is about 1.12 sigma. That's 1 sigma plus a little bit extra. So this you can use as a general rule for these situations involving a pair of neutrally charged atoms or molecules interacting with each other. The equilibrium distance, the distance where the attractive and repulsive forces cancel out and the total force is 0, is going to be occurring when the distance is about 1.12 times the diameter of the molecule, 1.12 sigma. Any questions on that so far? So with that out of the way, with all these facts about force, and let me make a note of that. Equilibrium is R naught is 1.12 sigma. So we're really splitting it up into R values less than 1.12 sigma, they're too close, and R values more than 1.12 sigma, they're further apart than that. But let's translate each of these statements about force into a statement about potential energy. Using what equation could we use for that? How are force and potential energy related to each other? What's the relationship between those quantities? Yes, or other way around, actually. Force is the potential energy divided by distance. And you can actually get this from the idea of work. Work is force times distance. But work is also the change in potential energy. If we assume we just take these, let's say we take these molecules and we move them some distance apart from each other, but keep them at a constant speed. You're doing work because you're applying a force as they move some distance. So the work you're doing is just changing the potential energy. And that force is the force you're applying. But the force you're applying is the opposite of the natural force. Like, for instance, let's say the particles are attracting each other. You have to pull them in the outwards direction to cancel out the inwards force. So the force you're applying is the opposite of the natural force. Also, I'm going to call this delta R in this case, because the distance we're talking about is R, the distance between molecules. Solve that for force, and what do you get? Or how would you isolate force here? Yeah, divide both sides by delta R. We also want to get rid of the negative. So let's divide both sides by negative delta R. And we get negative delta potential energy over delta R. So far, this is technically just an approximation because this is assuming force is constant, and the force is not constant here. The force changes as you move the molecules. But we can make this exact by rewriting the deltas as tiny, tiny changes. And tiny changes really means we're talking about a derivative. So this is really how these quantities are related. In general, any force associated with a potential energy, the force is equal to negative derivative of potential energy with respect to position or distance. In other words, the amount of force, the strength of the force, is talking about how much the potential energy changes per meter of distance. And the negative signifies direction. The negative means the force is going to be pointing towards lower potential energy. Any questions on that relationship so far? And ultimately, we're trying to build a graph of potential energy here. What does the derivative tell you about a graph? Is the instantaneous rate of change is what it means. What does that tell you about the graph, though? Like, how would you see on the graph that the derivative is the same or different or whatever? It's all about the slope, right? That the derivative of potential energy with respect to position, that is the slope of a potential energy versus position graph. So we can also say that the value of the force is equal to the opposite of the slope of the potential energy graph. Slope of potential energy graph is the opposite of the value of the force. So in general, the slope of the potential energy graph is going to be the opposite of the value of the force at every location, assuming this is the force that the potential energy is associated with. That means every one of these statements about the value of force can be changed into a statement about the slope of the potential energy at that location. For example, we know that the force is repulsive, greater than 0, if they're too close. If the force is greater than 0, what does that tell you about the slope of the potential energy graph? Positive force means what? I wouldn't necessarily say decreasing slope because that implies that the force is that the slope is changing in a certain way. I would say it's a negative slope, which means the function itself is a decreasing function. So the function is decreasing in the sense that it's getting lower and lower as you go from left to right. I would say the slope itself is a negative slope. So this means that if the particles are too close, In other words, if R is small, specifically if R is less than R naught, then the potential energy graph has negative slope. It's a decreasing function in that entire region because it has negative slope, because the force is positive. So a repulsive force means a positive force, which means a negative slope for the potential energy graph. Next force fact, we know that at equilibrium, when R is exactly R naught, we have zero force. So if the distance between the molecules right now happens to be exactly R naught, what does that tell you about the potential energy graph at that point? If the force is zero at that point, then what does that tell you? Yeah, specifically the slope is going to be zero, because the slope of potential energy is the negative value of force. If the value of force is zero, then the slope of potential energy is zero. And think back to calculus for a moment. If you know that at some location, the graph has slope zero, what kind of point are you looking at? Yeah, this is going to be a max or a min, or at least a possible candidate for a max or a min. So that's what we should expect to see here. If there's one location where the potential energy has a slope of zero, that suggests that's a maximum or minimum value. So we're going to hit a maximum value or a minimum value. And we can figure that out by taking a look at the slopes nearby. For example, if we take a look at the next section, if we're talking about kind of far apart, if the distance between particles right now is more than equilibrium distance, we know that the particles are attracting each other. We know the force is negative. And if the force is negative, what does that tell us? If the force is negative, then yeah, the potential energy graph will have positive slope. So that means if we're further apart than a certain distance, further away from each other than equilibrium, then that means potential energy will have a positive slope. Also, we know that as the particles get further and further apart, that force gets weaker. Force getting weaker and weaker and weaker means the slope is going to get flatter and flatter and flatter. We get a weaker and weaker slope. So it gets flatter further out. So these are all the facts we know about the slope of potential energy. Every fact we know about force can be translated directly into a fact we know about the slope of potential energy, just by using this fact that the slope of potential energy is the opposite of the value of force. And note that none of this tells us what the value of potential energy is. It just tells us the slope in that region. Any questions on these facts so far? So let's try using this to sketch that graph, now that we have all of these potential energy facts. And ultimately, we're going to be making a graph of radius versus potential energy. I'm not going to draw in the axes yet, though, because we want to fill in the axes last so we can choose where to put them. But if we just write out what we want, for a small r value, so that's further left on the graph, we're going to have a negative slope. There's going to be some single location where the slope is zero at that instant. And then after that, further to the right on the graph, larger values of r, we're going to have a positive slope, which tells us this is what type of critical point. If we're going from negative slope and then flattening out and then positive slope, what have we just hit there? Yeah, this is a minimum. So we can specifically say that at R equals R naught, when we're at equilibrium, potential energy is at minimum value. So this is the lowest potential energy is going to get. Strictly speaking, all we can say is that it's a local minimum. It goes down, comes to a stop, comes back up. It might go down further later on. We don't know that yet, except we know that from thereafter, the slope is always positive. It's never going to get dipped back down again. But we also know that it gets flatter and flatter. It's going to get flatter and flatter slope, approaching, getting closer and closer to zero force and therefore zero slope. On the other hand, if we go to the left, what would you expect to happen to the force if you try to push two molecules closer and closer to each other, trying to make them overlap completely? What would you expect to happen to the forces involved if you tried to do that? If you're trying to push the particles really close to each other, what happens to the forces? Yeah, it's going to repel, and it's going to repel stronger and stronger and stronger. You can't physically push the molecules into the same location because the forces get stronger and stronger without any limit. So if the radius gets very small, very close to zero, the repulsive forces get very, very strong, which means the potential energy graph gets very, very steep. So we end up with a shape more like this. As the particles get too close to each other, the repulsive force gets very strong, so you get a very steep graph. But as the particles get further and further, the attractive force gets weaker and weaker. So the positive slope gets flatter and flatter and flatter. And so we end up with a graph shaped like this. This is the characteristic shape of the Lennard-Jones potential energy graph because we need the potential energy slope to match all the information we're predicting about force. Any questions on that graph so far? And next we're going to put in some axes. I mentioned earlier we're not going to put in the axes at the beginning because we need some flexibility there. Because we have some options. The vertical axis we need to put at zero radius. Zero radius actually has a meaning. Zero radius would mean the particles are at the same location. That's actually going to be an asymptote here because the particles cannot physically be pushed into the exact same location. Doing so would require an infinite amount of energy, an infinite amount of work. So we're going to have the vertical axis here. This is the energy axis. As for the r-axis, we should usually put the r-axis at zero energy. But the thing is, we kind of have a choice here. There's not really a universal standard for what zero energy means. Like, for instance, for potential energy of gravity. What does it mean to have zero potential energy of gravity? If we just write out our usual potential energy of gravity formula, what would it mean for your potential energy of gravity to be 0 joules? Mathematically, how could this formula multiply out to 0 as a result? Are there any of these factors that could be 0? If you just got mass times gravity times height, and you know they multiply to 0, which one of those could be 0? Yeah, your height could be 0. You can't really have an object with 0 mass, and if you're near a planet, you can't have 0 gravity, but you can certainly have 0 height. The height of the object could be at 0 altitude. But what does 0 altitude mean? What does it mean for an object's height to be 0? Where is that object? what's the height that we usually call 0? Well, not necessarily initial height, because we can put the object at any height we want to start with. Usually the ground, right? We often treat the ground as height 0. But note that we don't have to. You could say, for instance, that the ceiling is height 0, and then ground is, let's say, 3 meters under that. So ground level would be at -3 meters, and the ceiling would be at height 0. Or let's say maybe you put sea level as height 0. Let's say you're in a town that's 100 meters above sea level. If you set sea level to y = 0, then ground level would be at y = 100. Or you could even set the center of the planet at y = 0, and then everything at ground level would be at whatever the radius of the planet is, plus or minus some fluctuations. But the important thing is there's no real reason why we have to call a certain location y = 0. Y = 0 is just a reference point we choose and measure everything from there, above or below. So 0 potential energy doesn't really mean anything specific, anything physical. 0 potential energy just means you're at the location we're calling the reference point. And it's the same idea here. We could choose any value of energy we want to call energy equals 0. We could say the bottom of the graph is 0 energy, or we could say way up here is 0 energy. We could pick any level of energy we want and say that's 0, and we're measuring everything from there. But one of the most important things about this graph is not just the low point, but this curve is getting flatter and flatter and flatter. So what would you say it's approaching? What do we call that if the curve is getting flatter and flatter and flatter? If there's some horizontal line that it's approaching. Generally, we call this an asymptote. If you've got some curve that's getting closer and closer and closer to some straight line, but never actually reaching it, that's the asymptote of this graph. And note that this graph also has a vertical asymptote. This curve is getting closer and closer and closer to this vertical line, but never reaching it. This portion of the curve is getting closer and closer to this horizontal line, but never reaching it. And generally, if a graph has an asymptote, that asymptote is probably one of the most important things about that graph. And so what we're going to do, since we have the option of choosing any location we want to call energy equals 0, we're going to use the asymptote as our reference point, our reference value. So the asymptote is what we're going to call 0 energy. Anything below the asymptote is a negative amount of energy. Anything above the asymptote is a positive amount of potential energy. And that asymptote will then be the r-axis. So that's our Lennard-Jones potential graph, including the axes. It's very steep on the left side, representing the extremely strong repulsive forces if the molecules are too close. It's a much gentler positive slope further out, representing the weaker attractive forces if they're further apart from each other. There's this one location called equilibrium, or R0, where the slope is 0 at that instant because the force is 0, so we get a minimum potential energy. And everywhere else, we can give some ideas about the force based on the slope. For instance, if we actually drew in some of the force arrows, out here, for example, what do you notice about the slope at this location? The slope of the potential energy graph is what? Yeah, we've got a positive slope. And if the slope is positive, then the force has to be, right, the force is going to be negative. In other words, the force is going to be pointing in the decreasing r direction. So the force is going to be, at this location, the force is in the getting closer to each other direction. Over here, slope is still positive, but it's a lot less steep. So we're going to have an attractive force, but much weaker, typically shown by drawing a smaller arrow. What about over here? What do you notice about the slope at this location? Over here, the slope is, yeah, we've got a negative slope. So that means the force is going to be the opposite of that. So the force will be positive. Also, since this is a very steep negative slope, that suggests a very strong positive force. So at this distance, when the particles are this far from each other, they're too close, so they're going to get a repulsive force that's very strong. And if you take a look close to equilibrium, close to this minimum value, all of these forces near equilibrium are pointing towards equilibrium. So what kind of equilibrium do we call that? If it's at equilibrium, it'll stay at rest forever. If it's somewhere near equilibrium, it gets pushed back towards equilibrium. What do we typically call that? Would you call that stable or unstable equilibrium? If everything nearby gets pushed back towards equilibrium. Yeah, this is stable equilibrium. Whereas unstable equilibrium would be if you had a potential energy graph that looked like this. This top point is technically equilibrium because all of the forces, the force at that location is 0. Let me color code that better. At this location, the force is 0. But if you take a look at the forces nearby, negative slope, positive force, negative slope, positive force, positive slope, negative force. All the forces nearby are pushing outwards, away from equilibrium. If you're a little bit to the right of equilibrium, you get pushed further to the right. If you're a little bit to the left, you get pushed further to the left. So that would be unstable equilibrium. But this one, if you're a little to the right of equilibrium, you get pushed back to the left. If you're a little to the left, you get pushed back to the right. Everything's pushing towards equilibrium, so that is stable. In the sense that you will tend to find molecules at this distance from each other. If they're too close, they get pushed away. If they're too far, they get pulled back towards. But if they're at that location and at rest, they can just stay there forever. Any questions on that so far? And so far, we've been looking at the potential energy. Let's try rethinking this and including kinetic energy this time. Because they're both energies, so we should be able to graph them both on this same graph. So we're going to have some low point here. And a graph that looks like this. And these are the axes of radius and energy. By the way, that low point is just going to be some tiny amount of negative energy. And that tiny amount of energy we usually call epsilon. So epsilon is just the amount of energy it takes between the asymptote and this low value. So epsilon is just some tiny amount of energy, tiny because we are talking about individual molecules. And since the minimum is epsilon below, we're going to call this -1 epsilon, negative epsilon. And we're going to treat epsilon as the unit of energy in the same way that we've been treating sigma as the unit of distance. So you can mark off this graph in units of epsilon. You're going to have negative epsilon, -2 epsilon, -1/2 epsilon, +1/2 epsilon, +1 epsilon, and so on. So the graph, the energy axis of the graph can be marked in units of epsilon. In the same way that the r-axis is marked in units of sigma. We got 1 sigma, 2 sigma, 3 sigma, and so on. And r-naught specifically is about 1.12 sigma. Any questions on that graph so far and the labels on it? And that is, of course, our potential energy graph. If we wanted to also graph kinetic energy, we're going to need a little more information. Because potential energy and kinetic energy What's the relationship between those? What should we expect those to add up to? Yeah, those add up to E total. So if we assume these particles are moving around, they're interacting with each other, but let's say they're not interacting with anything else, then we can treat this as a closed system. E total should be a constant. So let's say we have a value for E total. Let's say E total is, let's say negative 1/2 epsilon, because the energies in these cases are often going to be negative values as the total energy. Let's say E total is negative 1/2 epsilon. We should expect that to be a constant because we're assuming this is a closed system, which means it's just a flat horizontal line. And if you know potential energy and E total, you can solve for kinetic energy. In fact, we could just subtract PE from both sides. Kinetic energy is going to be E total minus potential energy. And some very important things to watch for on graphs like this. What's the lowest kinetic energy can possibly be? Not just in this situation, but any. Yeah, 0. Kinetic energy with the 1/2 mv squared as the usual formula can never be negative. So the lowest kinetic energy can be is 0. And what has to be true about E total and potential energy in order for kinetic energy to be negative? If you're subtracting two values and you get 0, what does that tell you about those two values? They got to be the same, yeah. So if you want to know where kinetic energy is 0, look for locations on the graph where E total and potential energy are the same. In other words, look for the intersections here and here. Those are locations, those are R values. At those R values, E total is all potential energy, so there's nothing left for kinetic energy. So at those two values, kinetic energy has to be 0. In between, potential energy goes down, so kinetic energy has to go up. In fact, where would you expect kinetic energy to be the highest? Right, when potential energy is the minimum, kinetic energy is going to be the maximum. And we can even tell how much, and then of course that will be at equilibrium, because that's where kinetic energy is highest, because potential energy is lowest. Kinetic energy is just the difference between E total and that potential energy value. So if we want to know the largest value of kinetic energy, just look for the largest difference between E total and potential energy. That difference is 1/2 epsilon. So 1/2 epsilon is going to be the value of kinetic energy at that location. In between, we can just mirror what potential energy is doing, because from here, as we go to the right, potential energy is decreasing, so kinetic energy has to increase to match at the same rate. Potential energy levels off to a minimum, so kinetic energy levels off to a maximum. Potential energy increases slowly, then quickly, then kind of starts to slow down. So kinetic energy also has to decrease slowly, then quickly, then kind of start to slow down. So the kinetic energy graph we can expect to look like this. It's essentially the potential energy graph flipped across the axis and shifted, because negative potential energy means the graph flipped across the axis, plus a constant means shifting it. So we're literally just flipping the graph across the axis, shifting it vertically by an amount equal to E total, and then of course cutting it off at 0 because kinetic energy can't be negative. So that's our complete kinetic energy graph. And one more bit of terminology. This far left point and this far right point would be called R min and R max, because that's the closest the particles can get together, and that's the furthest the particles can get together. At this energy level, the particles can't get closer than R min and can't get further than R max. They're stuck in that region. They can just oscillate. Any questions on that so far? So try getting some practice on this on your own. Either draw out a Lennard-Jones potential graph, this curve, or you should be able to find some copies of it online. Choose any E total you want. Just draw in a horizontal line at any level you want, and try finding R min and R max and drawing out the kinetic energy graph that matches that. It's a good way to get some more practice and some general intuition for how this system works. So give that a try to get some extra practice. Email me if you have any other questions, and I will see you next time. You're welcome.